and we're going to be doing a little bit more kind of advanced concepts. The first thing is going to talk about something, a data structure, if you like, called the stack. So lots and lots of processors use this concept of a stack. As it says there, it's an area of memory that's used for temporary storage, but it's a little bit unusual in that it, basically it has something called a pointer that points to, if you like, part of that storage, and the storage is considered to be organized in a certain way. So you can think of it traditionally as kind of like a stack of plates. You can store something else, and that anything you store goes on top. And when you want to take it off, you have to take it off from the top. You can't. You're not supposed to access things directly within it. Okay, so we might talk about it as being last in, first out. LIFO. And we have a pointer that points to the top of the stack of plates. And that's this thing called the stack pointer. In the 8051 family, the memory locations which are used, they form the stack of plates, are just part of the internal data memory. Now, refreshing your memory, in the 8051, the internal data memory goes from 00 hex through to technically FF hex, and between 00 and 7F hex, that's data memory that includes things like the register banks. So remember, you've got the 4 register banks here. And then on top of the register banks, you've got the bit addressable memory. And then you've got general purpose memory on top of that. The bit addressable memory starts at 20 and finishes at 2F. And above that, you've got this area called special function registers. If you have an 8052, you may well have, well, you will have another block of memory here sitting alongside the special function registers that you could only access with special instructions, indirect addressing. By default, so I'm going to ignore the slides for a few minutes and I'll just talk about this in general, and then we'll look back at the slides. By default, the stack pointer, when you switch on the 8051, points to location 07 hex. Okay. And in terms of putting something onto the stack, we give that a special name. To put on the stack, or place on the stack, we call that operation a push. And in the 8051, what happens when you push something is 2 things. 1, increment SP. SP short for stack pointer.
No.
And then insert value, if you like. To take something off the stack, so to remove from stack, that operation is known technically as popping. So you're pushing and popping. So when you pop the stack, 2 things happen. First thing is extract value. Second thing is decrement SP. And that's how it always works. So in the 8051, this, yeah?
Just repeat this again, please. Repeat this again, please.
Say it again?
Yeah.
So in the 8051, you can use part of the internal data memory as this special data structure known as a stack. Okay? So far so good? A stack is a data structure that has this form. Basically, think of it as a stack of memory locations, and you have a pointer always to the topmost value. Now, I'm going to show you, I'll go through the process. So, let's do that now. So initially, you've got a block of memory locations here inside the 8051, and this is part of this over here. And let's say this happens to be location 07, 08, 09, 0A, 0B, 0C, and so on. When you switch on the 8051, the stack pointer will have the value 07. It will be pointing to this memory location. You can't change that when you switch the power on. That's what Intel decided it would point at. So, let's say that you now wish to store some values in the stack. Now, typical things you might want to store are things that may be, for example, in a register bank. So, let's say that earlier we did this. We said, move into R0, immediately the value 01 hex. That's immediate addressing. We're saying take this numeric value, 01, and stick it into R0. Another instruction. Move into R1 immediately, 02 hex. Move into R2 immediately, 03 hex. So at that point in time, these locations 00, 01, 02 will actually contain those values. I'm not really bothered about that. Now let's consider what would happen if I was to write this. Push 0. Now, you might say, why is it not push R0 not? We don't bother with the R. But it effectively means push the contents of R0 onto the stack. It's actually saying push location 0 onto the stack. And we might do, for example, push 1, push 2. Now let's see what happens if I was to execute that little program to this bit of memory. Okay? When I execute push 0, the stack pointer is initially pointing to 07 in my internal data memory. But we do what it says to do up here. So step 1, add 1 to the stack. Well, 07, add 1 becomes 08. So the stack is now pointing to 08, and we would write into memory location 08 in this case, the location of memory location 0, which happened to have the value 01 in it. So this would end up with a 01 in there. The stack pointer at the end of this operation would be pointing, SP would have the value 08. So at the end of that operation, the stack pointer has the value 08. Let's do the same thing again, because we're doing this. Push 1. We follow the rules that it says over there, so you add 1 to the stack pointer. Well, 8 plus 1 becomes 9, and you put into the stack, in this case, the contents of memory location 1, register R1 actually. So that will have the value 02 would go in there. Automatically, at the end of that operation, the stack pointer will be updated to have, where are we? So we did 07 got it to here, 08 got it to here. Sorry, at the end of this, the stack pointer has the value 08. That's the end of that operation. What am I doing? Have I got that right? So it was 07, lost my train of thought now. Let me just, so it starts on 07, you increment and then store, which will put it at 08. We've done the same operation again, so add 1 to 8 becomes 09. And store, so stack pointer's pointing here. After the second operation. Just check that. So on the first one it had 07 by default. We hadn't performed a push. Doing the push, we add 1 to it and then store. So the stack pointer will have the value 08 and we'll be pointing here. On the second operation, we add 1 to it and store. So it'll have the value 09. On the third operation, we add 1 to the 09, which becomes 0A, and store at that location. So the SP will be pointing here with the value 0A, and we will store whatever this thing is. Yeah?
If 07 is not used by the stack, can we use it?
No, it's not. That's the trick.
Can we use it for anything else?
Yeah, of course you can.
Can you just put anything in there?
Yeah, and I'm going to explain that in a minute. I'll talk about, I'll come on to that. But yes, when we basically switch on the processor and the stack's pointing to 07, actually there's nothing in the stack at that time. So although the stack's pointing to the 07, it's 07's empty. And we always do things in this sequence. So as soon as you push, the first thing you do is increment. So if you want the stack to start at location 20x, the value you should store in it to start with, because you can change its initial value, would not be 20, it would be 1 less than 20. Knowing that the first thing that you do whenever you store anything is add 1 to it. So by default, the stack points to 07, which means the first location you will actually write to is not 07, it will be 1 more than 07 because of the rule here. We always increment before we store. Now you might say, well, I don't want my stack to be in that bit of memory, I want it to be somewhere else. And that's okay. And the way you do that is you can say, move into the stack pointer immediately a value. So let's say, if you put this value in, 20 hex, and I said, okay, now you're going to write to the stack, what's the first memory location you're going to use? It actually won't be 20, because the pushing operation always adds 1 to the stack before you store. So the first location that actually be used will be location 21. So I know you might think it's a bit confusing, but if you remember these rules, you won't get stuck. Yeah.
But it doesn't need to be empty for the point of location.
The assumption is that when you're initializing it, you haven't used the stack before, yes?
So but 07 isn't part of the stack, so you can come use it for...
Exactly. You can use it for anything you like. In fact, it's register R7, you might be using it for lots of important things. Now, and you're actually coming on to another point. Yeah.
Why would you do this process if you're not moved?
Why?
On that, on the last one you've written.
Yeah.
Why
This.
would you go to 21?
Right. I'll let. Well, but first of all, if I was to initialize the stack pointer with this value, and then I do a push, the rules of pushing say the first thing you do is add 1 to the stack pointer and then store.
Well, from that one you wouldn't go to.
It would basically, because if this has been initialized to 20, and you add 1 to 20, 20 plus 1 is 21, so the first location you would write to would be location 21. I'm not answering your question. You've got that kind of... It's just the way it works in this Intel processor that effectively the pushing operation, whatever's in the stack pointer, it doesn't push it to that location. It adds 1 to the stack pointer and then stores it. And you can't change that, that's just the way it is. Now, if you wanted it to start at location 20, your stack, instead of location 21, that's fine. Instead, all you do then is you initialize your stack to have the value 1f hex. And then, as soon as you do a push, add 1 to 1f, that becomes 20, and it will store at location 20. So the stack, now that's stored on the stack. And I'm going to come back to some of the questions that were raised earlier on about its location and the impact of that. But let's just put that to one side. Having put these things on the stack, to recover those values, I could just simply do, for example, pop, and then, for example, pop2 would then say, okay, whatever's in the stack, take that and store it back into register 2. And then I could do, for example, pop1, pop0. Now you might say, why am I bothering to do all of this? Good question. Let's say that I want to use these registers for some other purpose. I'm going to do lots of sort of register addressing, I'm going to manipulate them, put new data in them, but I don't want to lose their previous values. Now, one way that we could do that is we could do that register bank switching, maybe, which we've known we can do, changing the program status word. Another technique, if you want to store information temporarily and then recover it later, is to use the stack. What I'm doing here is I'm writing to the stack a sequence of values and then popping them back out and sticking them back where they came from. It absolutely matters that if this is the order you push them in, you have to pop them in reverse order. Otherwise the data will be delivered to the wrong places. So if you were to make the mistake of doing this, given that the stack is currently pointing here, when you pop 0, it'll be 03 that will be written back to R0, which actually wasn't the same value as it was before. So to make sure that you get things back out the stack and put them back where they belong, whatever you put on the stack in a certain sequence, you reverse the sequence to put them back where they were. Okay? Let's just have a look at a slide or two a minute, and then I'll... So this stack pointer always points to the top of the stack. And whenever you write to the stack, the operation for putting something on the stack is called push. Special instruction push. To take something off the stack, the operation is pop. When you push something onto the stack, you don't have to worry about the stack pointer being incremented. It happens automatically. The same way when you pop from the stack pointer will be decremented automatically. Okay? If you're happy with the stack to start from location 08, then you don't need to do anything. It will be initialized to 07, so the first time you do a push, the first location it will be written to will be location 08. If you don't want that and you want your stack somewhere else, then we can overwrite the stack pointer value with a different number, and that will become the new start of the stack. In fact, that number you write it with isn't ever going to be written to by the stack. It's always going to be one more than that. So I've mentioned about the initial value of stack pointer, and two operations that we use on the stack explicitly are push and pop. And down here I had the sequence of actions associated with each of those. So here's another example, a little bit of assembly language, and then it's showing you what's happening to the stack as a consequence of those instructions. So first of all, we've initialized R6, R1, and R4 to have these contents. Okay? And then we've said push the contents of location 6, register R6, onto the stack. Now, we haven't done anything about anything special moving the stack pointer. It's got its default initial value, 7. And I've said to you, when you push onto the stack, the first thing you do is add 1 to the value, and then you store it. So the first location we'll actually get written to is not location 7, it's location 8. And it will have this value. The second push says whatever's in R1, push that onto the stack. The stack pointer is currently got the value 8, but a push operation means add 1 to the stack pointer, then store it. 8 plus 1 becomes 9, so the 12 will be written to location 9. And the stack pointer will still have the value 9 at the end of that. Push 4 causes us to increment the stack pointer again, which makes it OA, and we will store this value at OA. And this is then showing you taking things back off the stack. Anything after a semicolon, this is just a comment, okay? That's not any assembly language. This is the assembly language, and this is the assembly language, and that's the assembly language. So if we had a stack that was currently looking like this, with the stack pointer with this value, and we were to execute this instruction pop3, what would happen would be we would go to the stack, take whatever's at that location, put it wherever we've been told to put it, and then decrement the stack pointer. So if it's OB, we'll go to location OB, get the contents of that memory location, which in this case is the value F4, and we will store that in register R3. Or if you like, direct memory address 03. When we follow that, and then at the end of that operation, the stack pointer will have changed its value. It will be 1 less, because when you pop something, you extract it, move it to wherever it's got to go to, then decrement the stack pointer. So if it started off with the value B, at the end of that operation, it will have the value A. So on the second pop, pop 7, effectively whatever's in the stack at that location will be put into register 7, and then this will be decremented again. So we'll then take the 3A, and that will go into R7, and then the stack pointer will drop down to 0, 9. I'll talk a little bit about this. This slide isn't absolutely 100% correct, so I'll point out the bits. So if you have the stack pointer initialized as Intel would like it initialized to 07 when you switch the power on, the first location you're going to use in the stack is location 08. So I think you're all happy with that now. Because when you do a push, you always increment, then store. When you pop, you extract, then decrement. You will notice that, and this is coming on to one of the questions that was asked. Let me blank this a minute. Let's have a zoom in of the internal data memory. So we've got, these are the locations, 00, 01, 02, 03, 04, 05, 06, 07, 08, 09, etc. And I've told you when you switch the power on, the stack pointer holds the value 07. Let's say that you are using register bank 1 for doing things. So you have some information that's stored in register bank 1, because remember, what we've got here is from here to here, this is R0, R1, R2, R3, R4, R5, R6, R7. That's reg bank 0. And then above that, we've got R0, R1, R2, R3, R4, R5, R6, R7.
Oops.
which will be register bank 1, and so on. Okay? Remember, there are 4 register banks. What this means is, given that the stack pointer points here to start with, if you want to start using the stack, and you are also using register bank 1 to do other things, you have a serious problem. Because when you start storing things in the stack, they're going to overwrite what was there before. So if you let the stack pointer stay as it normally is, when the default value, when you switch it on, basically the only register bank that it's safe to use is probably register bank 0, because the stack pointer is pointing above that bank of registers. If you keep on adding to the stack, you'll start overwriting the contents of register bank 1. If you keep on going, you'll overwrite the contents of register bank 2, and so on. Now you might say, well, not a problem, I don't mind overwriting register bank 1, I won't use that, I'll just use register bank 2. It is up to you to make sure that if you are using register bank 2 for your data, that you don't mistakenly allow the stack to grow so big that it starts overwriting your data. The microprocessor won't check for you. You as the programmer have to be disciplined and to test for this. And actually, the stack growing so big that it starts to overwrite data that you didn't expect causes really bizarre programming errors. You know, really strange behavior starts to happen, and it's very hard to work out what's going wrong. So, something to bear in mind. So you might say, well, I'd rather move the stack pointer out of the way somewhere safe, and that's fine. And I've shown you how you can move the stack pointer. Yeah?
So you can use unlimited amount of memory for a stack?
Not unlimited. You can only use the internal data memory.
But up to the end?
Up to the end, yes. Yeah. And in fact, I believe the stack will actually, if you've got an 8052, effectively the stack, accessing it is like doing indirect addressing. So that 128 bytes extra that you get alongside the special function registers, you can use it for the stack. But that's all you've got. So you can't store huge amounts of data in the stack. You've got very limited space, but it's a useful temporary store of information. You might say, well, why bother with a stack? Why not just store data in different places? The nice thing is when you're popping things, you don't have to worry where you're popping from. You don't have to explicitly give an address. Basically, it's implicit. It'll just take from wherever the pointer is, and then move the pointer down to the next one. And then when you take the next one, the pointer's already in the right place to take that one. So it's more efficient than manually just putting different pieces of information in different locations. Now, according to the slide, it says that you should. Oh, let's do another drawing. In fact, let's probably just about use this one. This is an example of the internal data memory in an 8051. The stack is going to start, if you're using it, at 07. So if you start using it at 07, you're going to be overwriting register bank 1 for sure. If it keeps growing, you'll overwrite register bank 2. If it keeps growing, you'll overwrite register bank 3. According to the slide, it says the stack can't use the bit addressable memory. That's not correct. You can use that area. So one thing you could do is you could move the stack pointer above the register banks and start pointing at location 20. Well, actually, you point to location 1F. But we tend not to do that because actually this bit addressable memory is very useful for other things. So although I didn't write the slide, but like I say, I have confirmed, I actually ran the assembly language this morning to double check. There's nothing to stop you from using the stack into the bit addressable memory. Yeah?
If you start at, say, R0,
yeah.
and keep pushing onto it, does it skip the next 3 banks? Or does it go to R0 on the next bank?
Well, in terms of the stack pointer itself, it's just a location. So when you say initialize it to the value 0.
Say you start R0, you do R1, R2, R3.
What you do, clarify what you mean by when you start.
Say you start the stack pointer, so you start at the stack pointer at R0.
Well, the stack pointer would have started at R0.